It's a pleasure for me to tell you a little bit about the capabilities in the ADF Modeling Suite. Today we'll tailor it towards what can be done in terms of modeling atomistic properties for understanding and improving materials. So as I already mentioned in the chat box, let me know if you have any questions and I'll try and see if I can answer them on the fly. I also just started a recording, so we can post the video after this. And I'll also make the slides available afterwards. Okay, so let's get started with the presentation. So here's the plan for today. I'll start with a short introduction of Amsterdam Density Functional itself and the company behind it, SCM, Software for Chemistry and Materials, and then we'll quickly delve into all the tools that we have available, and I'll try to sort of go by a few examples and see where ADF has been used or can be used to model material properties at the atomistic level. So within the ADF Modeling Suite, we have ADF for density functional theory for molecules. We have a periodic extension of that band, and we'll show some examples of how that can be used for studying electronic properties of 2D materials as well as optical properties. I won't talk too much about density functional base tight binding, but essentially it can do sort of the same things as ADF and band, but more approximately. And it's not as powerful as those two tools, but it's much faster, so you can study much larger systems. And then we'll end at the end with ReaxFF, Reactive Molecular Dynamics, which is one of the tools that we're developing strongly on, which has a number of interesting applications, especially in the materials area. And hopefully at the end we have some time for further discussions and questions. Okay, so SCM is based in Amsterdam. So I'm here sitting actually in the office of Evert-Jan Barends, who's the founding father. He essentially pioneered using density functional theory for chemistry, and together with Tom Ziegler, and they were already in the 70s propagating that one could use DFT as a computational chemistry tool to understand chemical properties of molecules, from spectroscopy to understanding catalysis. And at that time, DFT was well respected in the physics community, but not so much in the chemistry community. It wasn't until, let's say, the mid-90s that actually the chemists started using DFT as well, and by now I think it's safely established that density functional theory is a viable tool for modeling properties of molecules and materials. So SCM started off as a spin-off company, as I mentioned, from the Free University of Amsterdam, 1995, some 20 years ago, and we're still renting space here in the university, and we have strong collaborations here with the theoretical chemistry group, as well as many other academic groups worldwide. And currently we have about 15 people that work with SCM, and most of them actually did their PhD in computational physics or theoretical chemistry, and so they have a strong feeling that they really enjoy doing science, and that's also one of the points that I always like to stress, is that within the SCM team, we have many experts who actually write the code, and those are also the people that help you when you have any questions or problems, especially on the technical side. If you have any bug or problem, they typically know pretty quickly how to help you out with that. So that's one of the strong points. And these developers then, they do a lot of the boring work that people in academia don't want to do, or actually don't have the time to do anymore, because they need to write grant proposals, need to write papers and so on. So if they have any new functionality, They don't have the time to actually further debug that, optimize it, make sure it works on all types of platforms. So that's what our developers do. They take care of new functionality from external groups as well as from our own, and make sure that works as pleasantly as it can on and as user-friendly as it can on different platforms. All right, so let's go to what ADF can do. ADF is our molecular DFT code. That was the first code that we had, so written by Evjan Barens, mostly, of course, with a lot of input from other groups as well. There are many different DFT codes out there. What ADF is particularly strong at is when you're dealing with systems where relativistic effects matter and or where you're interested in spectroscopic properties. So going all the way from EPR to X-ray absorption, there are tools available in ADF to model those spectroscopic properties. And there's particular good ways of dealing with relativistic effects in these systems. So the core electronic properties that are important in EPR NMR, they're treated relatively well, especially for systems where you have heavy elements as well as electrons sitting close to the nucleus, which also have a relativistic, they need to be treated relativistically in properties such as X-ray absorption. Now, what I'll discuss today is actually some of the functionalities that are relevant for organic electronics, one of which is phosphorescence. So when a system relaxes from a triplet to the singlet state by emitting a photon, and that is by default relativistic effect. So you'd need to be able to include spin orbit coupling in combination with the excitation properties. Also of relevance for organic electronics is how the electrons move, and there are some features in ADF which are useful for that, in particular transfer integrals. So that's one aspect that I'll discuss today. And then also in terms of spectroscopic properties, ADF has been used a lot to understand the optical properties of nanoparticles as well as molecules sitting on nanoparticles. So I'll discuss a little bit of what's possible in ADF and what has been done in ADF as well. All right, so going to the organic electronics, this is a schematic of how a phosphorescent OLED or how an OLED material works. Typically, we would have a cathode and an anode which inject holes and electrons into the material. They meet each other inside the layer where you have emitters, and those emitters can then emit photons, and you get your luminescence. So if we zoom in into what's happening here in this emitting layer, you have a hole and electron finding each other. They recombine in an exciton, and by spin statistics, if you have two electrons finding each other, 25% of those excitons will be in a singlet state where the electrons are paired up, and 3/4 will be in a triplet state. And classically, or let's say non-relativistically, this triplet state is not allowed to relax into the ground state by emitting a photon. So this is strongly forbidden in a non-relativistic picture. Same thing holds true for going from a singlet state, an excited singlet state, to an excited triplet state via intersystem crossing. That's strictly forbidden in a non-relativistic picture. So if we didn't have relativistic effects in a classical OLED emitting device, we would only harvest 25% of the excitons and maximally in this fluorescence process. So what has been realized some 20 years ago is that if you have systems where you have transition metals, especially the 5D elements, where you have relativistic effects, you can get fast intersystem crossing as well as fast phosphorescence. So if you want to optimize a OLED material, then in the emitting layer, you can put these transition metal complexes, which make sure that they harvest all of the singlet states, and then actually you can get theoretically 100% of your excitons converted into photons. So if you want to optimize your OLED performance, one thing that you want to optimize is your phosphorescence rate. And for that, you need to be able to include spin-orbit coupling with the excitation properties. And here is a paper that describes that works well for a range of complexes spanning the 4D and the 5D transition metal complexes, where in blue, that's the calculated radiative lifetime of the triplet for relaxing to the singlet state, and in red is the experimentally calculated lifetime. So typically, especially for the faster emitting complexes, you would be well within in the order of magnitude in terms of predicting the radiative lifetime when you do this spin-orbit coupling TDDFT calculation with ADF. There's also a tutorial online, so if I post the slides, then you can click through that, or you can just Google for that. And so that guides you through the process of how to do these type of calculations. More recently, there's another class of OLED devices, which is based on TDDF, and that's moving away from transition metal complexes, but still spin-orbit coupling matters there. So these are typically organic materials, where in order to optimize the radiative rate, we want to minimize the singlet triplet gap. So that's just by doing regular excited state calculations with time-dependent DFT, but also you want to maximize the coupling between the triplet and the singlet state. So in TDDF materials, actually you go from the S1 state to the T1 state. From the T1 state, you go back to the S1 state, and then finally get the delayed fluorescence from that S1 state. I also mentioned that for the classical phosphorescent OLED emitters, you want to make sure that you optimize this process, this intersystem crossing. And in the next slide, I show a couple of examples of how these processes can be studied with tools available in ADF. And then finally, you also want to make sure that the holes and the electrons, they move as fastly as they can, or at least you want to get the right directionality when they're moving from the anode to the emitting layer, or from the cathode to the emitting layer when you talk about electrons. And then another number of coupling processes that matter, and some of these can already be tackled also with ADF, but these are very advanced features using so-called frozen density embedding formalism in ADF. If you want to learn more about that, just send me an email, and then I can discuss that further with you after the web presentation. Okay, so here are two papers where they use ADF to study intersystem crossing with spin-orbit coupling. This paper from 2014 studies this osmium emitter complex, and they study the spin-orbit coupling matrix elements between the singlet manifold and the triplet manifold, and they try to uncover some guiding rules on how you can get fast intersystem crossing. So if you're interested in learning about that, you can have a look at this paper here. What they find is that you want to make sure that the singlet and the triplet states are both metal to ligand charge transfer states, and they're involving different d orbitals, and that's essentially the same guiding principle as you have in organic systems, where you want to make sure that you have different singlet and triplet states in terms of orbital angular momentum. That's called the El-Sayed rule, and you can extend that to organometallics. What they also find in this paper is that the higher spin orbit coupling is actually from the higher lying singlet excited state. So you want to make sure, in order to maximize intersystem crossing rates, that at least your exciton is capable of occupying some of the higher lying excited singlet states in the singlet manifold. A similar conclusion has been reached in this recent paper. So I think this is just from last month, where this group in the University of Vienna have been able to actually do dynamical calculations of the first phosphorescent OLED emitter complex, this ruthenium complex, where they have an interface between this non-adiabatic code called SHARC with ADF, where they can include spin-orbit coupling. So essentially what you do is you excite your molecule to the excited state, so that would be your excited singlet state, and then you let the system sort of follow its way across the multitude of different pathways it can take. So it can go to different singlet states, and if you include spin-orbit coupling, it can also go to different triplet states. And so in this study, they find that indeed you can get efficient intersystem crossing, but that intersystem crossing typically takes place from the higher occupied singlet states. And so, oops, sorry about that. And so the intersystem crossing rate is in the order of a couple of dozen of femtoseconds. So these two studies have the same conclusion. This study quantifies the intersystem crossing rate a little bit further by actually running the dynamics. All right, so then 2 slides on how you can calculate the Hall and electromobility. So by and large, people use the hopping transport mechanism to study mobility in organic materials. There are a number of other possibilities as well. So if you have crystalline material, you can calculate the effective mass tensors in our periodic DFT code. That usually only holds up for crystalline systems at low temperatures. So usually you're in the independent charge hopping event regime, where this hopping transport can be calculated from the transfer integrals, which you calculate with ADF, and then you plug that into the rate equations. And there's a more advanced way of calculating the electronic couplings, and that's using subsystem DFT or frozen density embedding. Again, a little bit more advanced. There's actually a good web presentation on that from Michele Pavanello. If you're interested, I'm happy to send you more information on how that works and what are the advantages of using that method. Right, so this charge transfer integral method that's available in ADF since already some 15 years is based on treating your system as consisting of 2 different fragments between which you can move an electron or a hole. And I'll just make a short demonstration of how that works in a minute. Here's a paper that actually describes the process pretty well in 2009, where they study a number of organic semiconductor materials, and in general they find reasonable agreement between the calculated mobilities and the experimental ones. So for this particular material, they picked all the different dimeric configurations and then calculate the electronic coupling. This you get straight out of ADF, plug that into the rate equation, and then finally, if you average over all those rates, you can calculate the mobility. And so in blue here, this is the theoretical charge mobility on a polar plot, and in general that corresponds reasonably well to the experimental results. Usually you find that you're within, let's say, 20 to 30%, and what you describe really well here is the anisotropicity. So the mobility is really high in this direction, but it's less high in the other direction. I don't know if you actually copied the crystal structure picture okay here. Okay, so let me just show you how that works. I go out of this presentation and I open up ADF. And then I'll make a new input file. And so for this example, we'll start with naphthalene. So I'll import coordinates from a CIF file on my desktop. So that's naphthalene. And so this is the periodic representation of naphthalene. the graphical interface will always go immediately to the periodic code if it recognizes it's a periodic structure. Now in this case, we want to cut a dimer, and you can see that there's no dimer in the unit cell, so we need to make a little bit bigger unit cell. So let's make a 2x2 unit cell, and that allows us to actually pick a set of dimers. So now we go to ADF, so we switch from band to ADF, and now we have a molecular representation, and we select two molecules here. So I choose select molecules. So I've selected two atoms into molecules, adjacent molecules, and that is now the dimer that I want to calculate the hopping rate for, or at least the electronic coupling, the charge transfer integrals. So I invert the selection and then delete all those atoms that I'm not interested in. Now I have to define the two fragments between which I want to calculate the charge transfer integrals. So we go to model regions. We delete this. So by default, anything that's imported is defined as a region. And we define this molecule here as region 1. And then we select the other molecule. So that's Control M or Command M on your MacBook. And that's region 2. And then we say in the multi-level fragments that we want to do a fragment calculation. And this fragment calculation can then be used to calculate the charge transport properties. So in the properties charge transport, we select charge transfer integrals. That's it. Now usually for these type of calculations, PW91 shows good agreement, but you can look into literature what other people have done as well. And for the sake of making it a little bit faster, I choose a basic numerical quality and double zeta and polarization function. That should give reasonably okay results. Now we run this guy. So we call this transfer integral. And now you get a prompt that actually charge transfer integrals needs no sim. So the graphical interface tells you that it has switched to no sim. That's good, because otherwise the calculation won't run. Now we see it popping up here in the graphical interface, the ADF jobs. This is the main job, and it has two dependencies, region 1 and region 2, which it will calculate first for you. Now in this case, we could have saved ourselves a little bit of time, because this molecule was the same as that molecule, so I could actually have defined one region and split that by molecule, and then it would transform the calculation from the one molecule to the other by rotating and translating that. So that makes sense if you have larger systems where you want to calculate these transfer integrals, save yourself a little bit of time. Okay, so now it's calculating from these fragments, calculating the FOC matrix elements between the HOMO on the one fragment and the HOMO on the other fragment for the Hall. And for the electron, it's calculating the LUMO, the FOC matrix elements between the two LUMOs. It's actually done. Now it's just calculating the final energy of that system. And when that's done, we can go to the output file, so SCM output. And we go properties. There should be charge transfer integrals there. And then it just prints, I hope you can see this, that it's not too small. It just prints the electronic coupling for the Hall transfer and for the electron transfer. And these are the terms that go into this generalized charge transfer integral. So this equation here. But what you're really interested in is the electronic coupling V, which goes into the rate equation. All right, so let's continue. And yeah, okay. So this is also, not only do we have something nice for organic LEDs, we also have a nice capability for inorganic LEDs, and that's using ligand field DFT. There's also a hands-on example available on how to do that. That allows you to calculate transitions between F and D electrons in lanthanide doped ceramics. So if you're interested in that, again, I might have to get you started in that area. All right, so okay, so we have a question in the meantime from Rafael Berger. What to do when you have a small ring of monomers, say 4? Okay, so that's not possible with the charge transfer integral. So there you always have to calculate the charge transfer event between 2 fragments. If you have more fragments, then you can use this frozen density embedding approach, where you can have any number of molecules embedding the event, embedding the central dimer. So Rafael, I will send you some more information on how to do that with the frozen density embedding approach from Pavanello. Okay, so moving on then to how you can use ADF for studying optical properties of nanoparticles. ADF has been used already a long time because it's efficient TDDFT implementations, specifically being able to deal with symmetry. So already with really modest computers, you could tackle really large gold and silver nanoparticles if they had symmetry. Then there's also a good way of dealing with relativistic effects, right? So this the Zora Hamiltonian zero order regular approximation. If you don't have very strong explicit spin orbit effects, you can use a scalar relativistic approach, which is just as cheap as doing the normal non-relativistic approach, but it's very accurate and efficient for these type of systems. Furthermore, in ADF, there's a specialistic exchange correlation model potential, statistical average of orbital potentials, SAOP, which turns out to be particularly well suited for studying optical properties of any type of systems, but particularly nanoparticles. That's because it has the right long-range behavior as opposed to the typical density functional exchange correlation functionals that you would use. Same holds true for the orbital, so the linear combination of atomic orbitals that you usually use in density functional theory. In ADF, we use Slater type orbitals, which fall off as an exponential, which has a different long-range behavior, the one that corresponds actually to the atomistic behavior of the exact, solving the exact Schrodinger equation for the hydrogenic systems, as opposed to other codes where typically we use Gaussian type orbitals, which fall off much quicker than the exponentials used in ADF, the Slater type orbitals. So through having this specific set of technical settings in ADF, ADF has been used for a long time with satisfactory results for studying optical properties of nanoparticles. And there are many groups who've been using this and are still using this for some time. So I'm just mentioning a few. So it's the ICONS group, Chivkana, George Schatz, Mauro Steiner, but many other groups have been using ADF as well for studying typically silver and gold nanoparticles. So here just 2 examples from, I think this is the Steiner group. So this is a gold nanoparticle capped with sulfur groups, and comparing here the experimental UV-vis absorption spectrum and the calculated one. So you can see it's pretty reasonable agreement. And here's an optical spectrum of a large silver nanoparticle of a few hundred atoms. And at that time, they were able to do that because it had high symmetry. But actually, what they've been working on the last 2 years, again, this is the Trieste, is making even faster TDDFT approach, which also allows you to go to larger systems and go to much higher excitation energies. So it's a different way of doing the linear response TDDFT. It gets rid of this bottleneck that you typically have in the Davidson diagonalization algorithm. You get rid of the memory bottleneck that you have, and what it does, it uses the polarizability and using an auxiliary basis set to calculate that polarizability matrix. So here's a paper that describes the algorithm and some applications, and just to give you an idea of what it can do. So these are calculations on, I think it's a 12-core desktop machine on these particular nanoparticles here on the right-hand side. So what was physically possible with the old linear response DFT for these three different complexes, they couldn't go to higher excitation energies. So these are the dashed lines here, blue, green, and red, because they run into this memory bottleneck. So using their new complex polarizability algorithm, they can go to much higher excitation energies, and you see you get the same shape. You get the first plasmon, you get the same shape out of that by using this complex polarizability algorithm. But you can go to much higher excitation energies. And what's really interesting here for this nitro compound in blue is that you get first a dip, so you think you're over, this is your plasmon, but then actually you get a plasmon rebirthing at much higher energy. If you're interested in running these type of calculations, I understood it's already available in our public releases, but it's not yet documented. So if you want to try it out, send me an email and I'll try to help you on your way with that. But still, we need to make sure that it works well. And so it's not guaranteed to work for any type of system yet. All right, so another interesting feature in ADF for nanoparticles is where you're actually looking at atomic systems sitting on large metallo nanoparticles, which is from the group of Jensen at Penn State, where they use so-called coupled approach, so where you couple the excited state properties of a molecule with the excited state properties of the nanoparticle, where you treat the nanoparticle using atomistic potentials, but including the full electrodynamics. And that's called the discrete interaction model, where each one of these atoms essentially has its own capacitance and polarizability. And you solve the electrodynamical equations for the two systems coupled together. So essentially, you embed the excited states of the molecules in the electrodynamical response of the nanoparticles. So that gives rise to really interesting properties. So you can look at things like plasmon-exciton hybridization. You can, for instance, calculate how the orientation of a molecule affects the absorption properties. So typically, if you're in sync with the plasmon, then you get much higher. So in this case, the excitation properties of the guanidine in sync with the plasmon, and you get much higher excitation intensities. So obviously, yeah, so surface-enhanced Raman is following the same principles, and it has recently been extended to optical active surface-enhanced Raman, so OA, and surface-enhanced hyper Raman. So there's still new methods being developed there, which giving access to much more sensitive properties in this surface-enhanced Raman and hyper Raman field. So this is the example showing the surface-enhanced Raman optical activity. If you're interested in learning more about that, this is really a new technique, also experimentally, and it's now also available computationally. So people are still trying to learn what can be done with that. But it's a really sensitive technique to get the, it can be used as a tool to get the absolute configuration of chiral molecules. That's a paper here in 2014. So even newer is this surface-enhanced hyper Raman. So this was published last year. It's available in ADF as well. So using the same coupling of the electrodynamical response of a nanoparticle with the excited state properties of the molecule, but now getting higher order excitations through down to quadratic response theory, you can calculate surface enhanced hyper-Raman scattering. Here's an example for aromatic molecule sitting on a few thousand atom silver nanoparticle. These are the experimental measured hyper-Raman spectra, and these are the calculated ones. So in principle, reasonable agreement here, but on the lower end, you don't get the lower modes as well. All right, so I realized I've been talking for quite some time about ADF, so I'm going to go a little bit quicker through our periodic DFT code, which is called band. It does a lot of the same things as ADF, so it can calculate a lot of spectroscopic properties and electronic properties, and I'm going to talk you through a couple of examples of where band has unique properties. So just to compare band, which uses the same Slater type orbitals as ADF, or you can even use numerical atomic orbitals with plane wave codes. There are a number of advantages that we use the Slater type orbitals. There are also a number of disadvantages. So what's advantageous about using Slater type orbitals is that you can do the same calculation on a periodic system as you can do on a cluster. So you can compare actually when you do the two type of calculations with ADF and band, what are the actual influences of going to a periodic system, either bulk or surface or QB. Also, we don't have with pseudopotentials, so we can treat all the elements in the periodic table all the way from hydrogen to 118. We can also include all the electrons in the core, so you can look at core Hall states, all these kind of things. Since we have already the orbitals, it's easy to do orbital analysis. You can do fat bands, I'll show that in a minute. You can also easily analyze the densities, so you can do atoms and molecules, calculate any sort of density properties relatively easily. And then many exchange correlation functionals available. All right, so the non-equilibrium Green's function implementation in band from the Josteisen group in band is particularly powerful. I don't know too much about it, but I'll try to give you some examples on what that has been used for. So it can be done self-consistently, including gate and or bias potentials, and since recently you can also do spin transport with this NEGF. Another advantage of using atom-centered basis functions is that when you have a two-dimensional system, you can treat it as a two-dimensional system, not so much with plane wave codes where you need to repeat it in the third dimension. So that has a number of advantages that you can treat it as 2D systems, and particularly for 2D electronics, that makes a huge difference, as I'll show in a few slides from now. Also, if you're already familiar with using ADF, then switching to band is relatively straightforward. You can use the same graphical interface to set up your system. In fact, I just showed you that you can switch from band to ADF in just one click. Okay, so I mentioned for 2D electronic systems, having the capability of treating it as a proper 2D system makes a huge difference if you're interested in the effect of fields on the band structure and ultimately, of course, the conducting properties of your system. So here's an example from a few years back from our collaborators, the Heine Group, now in Leipzig. They're really interested in these so-called Moses materials, so transition metals with chalcogenides, so typical examples being molybdenum and tungsten, and selenide and sulfide. So this is molybdenum disulfide, it's a monolayer, and looking at what the band structure of this material does if you apply a homogeneous electric field to it. So you apply that in the Z direction, and what that does obviously is polarize your system. So it pushes electrons in the direction of the electric field, and that gives rise to changes in the band structure. So if you go from 0 field to a very high field of 6.5 volts per angstrom, actually you start closing this band gap. So at 0 field, the band gap is a little bit too low, well known from density functional theory approximations. And you make it a metallic state at a really high field strength. You do the same type of calculation with a periodic, a 3D periodic code, so plane wave codes, then you cannot apply a homogeneous field, so you'd have to apply so-called sawtooth potential across the unit cell. And for any plane wave code, that just gives wrong behavior for the band structures under electric field conditions. So if you're interested in calculating how your material changes these electronic properties under a homogeneous field, if it's 2D material, you want to use a code that can actually treat your system as a 2D material. All right. So also relatively new, actually, in this year's release, is that we can also calculate the optical properties of 2D systems. So that's work from Mark Raupach, and he did an excellent work in actually modernizing the response code in our periodic code band. So in this case, we're not using linear response, TDDFT, but we're using time-dependent current density functional theory, which is theoretically a little bit more sound to do for periodic systems. But essentially what you get out of it is the dielectric response function. And so since 2017, you can also apply that to two-dimensional systems. So you can see the difference between, in this case, the dielectric function in the x-axis direction for bulk zinc oxide, and in this case for reconstructed monolayer of zinc oxide. And so you can calculate the properties, electronic properties of two-dimensional materials as well, the optical response of that. Then I mentioned this non-equilibrium Green's function in band. This is particularly powerful, and so there are numerous applications from the groups in Delft where they're applying this NEGF in band to the systems that they study experimentally. Typically, they have a break junction set up where you have a single molecule wedged in between two conducting electrodes, and then you try to manipulate that single molecule mechanically by pushing the two electrodes together, or usually use a tip to do that, and then see what is the effect on the conductivity through that molecule and the single molecule junction. And so they have implemented the NEGF in band because they liked using an atomic orbital code for that. They can do proper two-dimensional boundary conditions. They can do self-consistent field during the NEGF, applying biases, and they can analyze the orbital levels during the NEGF. And so here's an example from a few years back where they had a really spectacular example on how they can tune the image charge effects in these single molecule junctions and explain that from running the calculations with the NEGF band code. So more recently, they can also do spin transport using the same NEGF module in ADF. And again, they had a really nice experiment. This is an iron molecule, which is in a low spin state if it's in a particular configuration, but if you stretch that configuration, the high spin state is preferred. And so that's depicted here. And so you go at a certain stretching, you go to a high spin state, and that high spin state has a higher transport propensity than the low spin state. So actually, if you start moving the electrodes further apart, you get the counterintuitive effect that you get a larger conductivity. So normally with the single molecule junction, this is tunneling transport. So if you have a shorter distance, you would expect higher conductivity, but because of this spin switch over, you actually increase the conductivity if you stretch the system. And this is a cartoon of how that's done experimentally. So this is the the electrode that they just push, and then they try to separate the molecules onto those two tips. And then finally, when it's attached, you can measure the conductivity. You can measure how the conductivity increases actually if you stretch it beyond a certain point where you have this spin crossover. So a really interesting paper. It's published in Nano Letters last year. So if you're interested in learning more about that, I can also send you more information on that particular experiment and calculations. Okay, so then we have also, I mentioned in the beginning, we have this density functional base tight binding, which can do a lot of the same things as ADF and band, but much more quickly in an approximate way. And so in a nutshell, what density functional base tight binding does is it uses a nearest neighbor approximation. So you only take into account matrix elements between atoms that sit next to each other, use a minimal basis set approximation, so you don't get any of the higher orbitals or lower orbitals involved. And then finally, you look up all the matrix elements that you need from a table, so-called Slater-Coster file. And that table has been pre-calculated with DFT. So once you've done that, you just look it up in a table, and away you go, and the calculation is done in a whiz. So with that, it's much faster than DFT, but also since you need these parameters, you cannot always calculate it for all the systems of interest. So if you're interested in doing geometry optimization, properties such as vibrations, vibrationally resolved excitation, so Frank-Condon factors, phonons, and so on, at the moment, only the elements in dark green can be calculated with this so-called quasi-nano set. Whereas if you're only interested in the band structures or UV-vis properties or electron transfer properties with NEGF, then you can calculate all those dark green elements as well as the light green elements. And so you can calculate optical properties of almost all the elements in the periodic table. Again, just a simple demonstration of how that works in practice, and this is just a thought experiment. This is palladium sulfide. It's an interesting material because essentially when you have more than one monolayer, it becomes semi-metallic, and more specifically, if it's a bilayer, so if you have two of those layers, it's almost like graphene. So it's semi-metallic. So it has a zero band gap with a very low density of states. Whereas if it's a monolayer, it's semi-conducting. So if you can think of a setup where you have first a bilayer, then a monolayer, and then a bilayer again, then you can imagine if you apply a gate voltage, then you can use this as a diode material. And so in this paper here, they demonstrate that with using DFTB and NEGF in the ADF Modeling Suite, and they calculate the IV characteristics for a different number of biases, and they can indeed demonstrate that there's a channel length of about 2.5 nanometers, which you can use to tune and make this diode material, and you can tune the characteristics by applying this bias over the gate. Right, so you can also calculate transmissions through thin layers. So for instance, you can wedge a layer in between gold electrodes and calculate the IV characteristics. And since you can calculate these excited states relatively quickly, you can calculate very large systems, calculate the optical properties of that, but they're only as good as the parameters are for this type of optical excitation. So this is just an example. While I ran these calculations a couple of months back, you can take a block of zinc oxide, 5 by 5 by 5 unit cells, and then that takes about 3 minutes on my MacBook here to calculate the lowest 100 excitations. So it can be a good way of pre-screening optical properties of nanomaterials as well. Okay, so now we move away from the electronic structure methods. We go to the reactive molecular dynamics, ReaxFF, that uses atomistic potential. So before I explain how that works and what it does, let me give you a couple of examples of where that has been used recently to study different materials, different properties. So on the top left here, we have a lithium battery, and I think I have a slide on how that works in more detail later on, where they have been able to describe how having a protective Teflon layer here can protect your electrolyte material. So there's the carbon nanotube electrode, Teflon layer here, and there's the electrolyte. So this Teflon layer actually protects your electrolyte from exploding, so that's a good thing. Here's an example of looking at hydrogen embrittlement. So this is alpha steel, and this is the hydrogen trajectory there. So looking at how the hydrogen moves inside the material and how it starts creating a crack and how it propagates is important to understand, the point where these materials start to embrittle and break. Here's an example of looking at nanoparticle formation. So a study from 2014, where they have titanium dioxide nanoparticles sitting in an aqueous environment, and when they meet each other, they have time actually, so they sort of bounce, rebounds. They have time to sort of heal in the right direction and start forming crystals in the right facet direction. If you do that in vacuum, actually you start just forming patched structures, and you don't actually start forming a nanocrystalline material. So in this paper, they were able to show that through the aqueous environment, the nanoparticles have a little bit more interaction with the environment, and they don't stick immediately to where they meet each other. So if they have time to realign and start forming the best crystal facet direction for forming larger nanoparticles. And this one I also talk about a little bit more in detail later on, but that's looking at a palladium nanoparticle doing catalysis under ambient, or actually reactor pressures and temperatures. Okay, so the idea behind ReaxFF is that you want to be able to study complex systems that are of interest in chemical engineering, chemical industry, model them atomistically at realistic scales. So there's no way that you can do that with electronic structure methods. So you have to go to atomistic potentials. And the idea in ReaxFF is that you move away from the standard harmonic force fields, but you use so-called bond order based potentials, where you calculate the bond orders dynamically every step you propagate in time. So in a harmonic force field, you can never stretch a bond because the energy becomes infinite to the point that it breaks. Whereas if you have this bond order based potential, then you can start breaking a bond. So going from a triple bond to a single bond to a zero bond, so where the bond is properly broken, is a smooth process in ReaxFF. And the other crucial idea behind ReaxFF is that you calculate the charges, you equilibrate the charges every step, charge equilibration. So this bond order and charge equilibration are the two main ingredients for ReaxFF, which makes it work, and you can actually study large complex systems where you can have chemical bond formation as well as bond breaking. Okay, so the rules behind ReaxFF are that because you want to do molecular dynamics, you want to have a smooth description of the energies as well as the forces, so you don't want any discontinuities. Also, you don't want to predefine which atom is going to react with which other atom, so you don't want to predefine which atom is going to be reactive or which molecules are going to react together. So we just want one atom type per element, and we want the ReaxFF force field being able to describe when it's going to react when it's in the neighborhood of other elements. So we don't want to predefine what's going to happen. That makes it a very complex force field, and I won't bore you with all the details, but the system energy consists of a large number of terms, and already each bonded terms consist of 16 different parameters, which makes it a pretty difficult force field to optimize. And so it's not trivial to make new and improved force fields for running reactive molecular dynamics. So again, that makes it one of the currently one of the, I guess, hurdles to start using ReaxFF more frequently for studying these large systems where you're interested in the dynamics of your system. So what we try to do is help within the ADF modeling suite as best as we can. So when you set up your system, there's a check saying, okay, these are the force fields available. Perhaps some of the parameters are not available. And there's also a move towards making it easier to optimize your own force field. And so in ADF, we have this MCFF optimizer, which allows you to build your own force field and re-optimize that. But currently still the best way of getting new parameters is collaborating with the two world-leading experts in this area. So it's Arie van Duin, who developed ReaxFF, and it was first published when he was at Caltech in the group of Bill Goddard, and so he's one of the other gurus on ReaxFF. But there are a number of other groups as well who are getting into this game, most of which sprung off the Caltech group, if you will, but other groups are getting into the game of making new ReaxFF parameters as well. So currently in ADF 2017, there's 79 different parameter sets spanning 38 elements. And so in orange, these are the elements available. But if you at random pick 3 elements, let's say sodium, vanadium, germanium, then there's not going to be a parameter set available that would be able to treat those 3 elements together. So you need to make sure that what you want to study is actually something that there's a force field available for, and also that force field is sort of capable of describing your system of interest. Okay, so besides actually running ReaxFF, there are a number of tools available also in the ADF modeling suite. And so I just want to highlight a few here. So one tool is called ChemTracer, Chemical Trajectory Analyzer, and that is capable of, after you run your reactive molecular dynamics, try and trace how one molecule transforms into the other, and do that in an automatic way. And once you have the sort of transformation pathway, then it also automatically calculates the rates of the reactions. So there's actually a pretty good tutorial on how to do that for burning methane, and you will find even for simple reactions such as methane burning with oxygen, there are already 300-400 different reactions taking place. So it's very complex to analyze that by yourself. So this automated way of doing that, but just looking at the bond order table, is a good way of gaining some insight into how the complex kinetic reaction pathway works. Then we have this molecule gun that was already available in the standalone ReaxFF, but now we made graphical user interface support for that as well. And that molecule gun allows you to determine how molecules are added in time. So for instance, if you're interested in wetting a surface, you can have the molecule gun here, and then at a certain randomized way, make sure that molecules make their way onto the surface. At certain intervals, you add more molecules, and so you can study things like chemical vapor deposition, surface wetting, or even how your material is resilient towards high impact from molecules and atoms. I have a little video on how that works as well later on, which also demonstrates this force biased Monte Carlo, which is a way of speeding up speeding up your kinetics of your system. So what it does, it sort of moves your system upwards against the force, and by that give you larger probability of actually going over reaction barriers. I have a slide on how that works later on. So that is used to speed up the kinetics of your system. Then we also have grand canonical Monte Carlo, and that's used to speed up the thermodynamics of your system. So as I mentioned, that can be used, for instance, to study how a catalytic nanoparticle works under reaction conditions. So you equilibrate your system under given temperature and pressure conditions. So in this case is a palladium particle. Then you want to get the actually catalytic structure of that particle under reaction conditions under different oxygen pressure, partial pressures, and temperature conditions. So at low oxygen pressure, that's going to be a surface oxide, whereas at higher oxygen pressure, that's going to be more like a palladium oxide. And those will have different catalytic properties. So by doing first this grand canonical Monte Carlo, actually in combination with ReaxFF, and then having your stable nano catalyst under reaction conditions, then you can run reactive molecular dynamics and see, in this case, how that affects carbon-oxygen oxidation to CO2. And then I mentioned already this Monte Carlo optimizer, so there's a tool available also for parameterizing or reparameterizing your own ReaxFF force field. And there's an advanced example on how to do that, actually make your first bromine force field. All right, so this I just discussed. Now a little bit more about this force bias Monte Carlo. So if you just use temperature accelerated MD, this is what I call it. So if you want to see things happening, you can just ramp up the temperature. If you start adding carbon atoms to a nickel particle to mimic what happens in a plasma when you're growing carbon nanotubes, you'll get a highly erratic structure. Whereas if you do electrodynamics alternating with this force bias Monte Carlo, you can run at lower temperatures and still see reactions happening. You actually start forming a carbon nanotube that is a little bit more in sync with what you see experimentally. So you get much larger number of carbon atoms per ring. Okay, so I see a question from Raphael Berger in the meantime. So how is the temperature set in this simulation? So that depends on what type of ensemble you use. So you can use an MPT ensemble or an MVT ensemble, and then you can use different thermostats and barostats for that. And so also with the force biased Monte Carlo, you can use a higher temperature as well. But you can also, because you get your kinetics faster, you can use a lower temperature and you get the kinetics which are more congruent with the actual conditions under which you do your experiments. Indeed, so you can use the same thermostats and barostats you can use in standard molecular dynamics. All right, so in a little bit more detail about this carbon nanotube formation. So once you run this force bias Monte Carlo, you can get a little bit more insight in how you start forming these carbon nanotubes, and you get a little bit insight in how the first stages of the carbon nanotube formation work. And so that's depicted here. If you're interested in reading a little bit more about that, the paper. So this is from the group of Eric Knights at the University of Antwerp. We've done a lot of interesting studies looking at nanotube formation in plasmas. Right, so then I think I've got 2 or 3 slides on how. No, wait, I want to show a video first. So just to give you an idea of how things change when you move from temperature accelerated dynamics to force biased Monte Carlo. And let me we go to my desktop, and there's a little video here. And first, actually, we use the molecule gun to shoot a buckyball and a graphene sheet. And then we create a defect here at the center of the graphene sheet, which then is subsequently used to simulate the self-healing. In this case, we're running the simulations at the same temperature, 900 Kelvin. So still relatively high temperature, but in this case, we combine it with force bias Monte Carlo, and you can see you can already start reforming some of the central rings here as we just use the normal MD. Still, the barriers are too high to actually see things happening within a couple of picoseconds. All right, so that was fun. Let's go back to the presentation and then go to batteries with ReaxFF, which is going to be the last thing I talk about. So I already mentioned this when I started talking about ReaxFF. Here's a little bit more details of the study. So carbon nanotube, lithium shooting out of it, going to the sulfur anode and through the electrolyte. Now, since you have these discharges, you have the lithiums coming out pretty hot. That heats up your system. As you can see, the system goes up to over 1,000 Kelvin here. And that means that actually your electrolyte is breaking. So through heating up your system, you start breaking your electrolyte, you start forming ethane and other gases, and that means that your electrolyte is actually wanting to explode, which is not good. So what you can do, a protective layer in between, Teflon being the obvious choice, or something other resilient as well. And what that does is it doesn't cool down the system. As you can see, you can still get up to 1,000 Kelvin, but Teflon is still not breaking at 1,000 Kelvin. So the lithium atoms are slowed down until they reach a temperature of a couple of hundred Kelvin, and then they're cool enough that they can move through the electrolyte to the sulfur anode without actually breaking your electrolyte. So that's a good thing. So that's using ReaxFF to getting insight in how you can actually protect your electrolyte by slowing down your lithium atoms with a protective layer. And that's shown here in a little bit more detail. So in green, you see the trajectories of the lithium atoms at around 450 picoseconds. So you can see if you don't have a protective layer, they move a little bit faster. And in doing so, they still have a high temperature and are amenable to decompose the electrolyte. Whereas this Teflon layer slows down the lithiums and makes the lithium trajectory a little bit slower, but still you have high enough charge mobility in this case to get a good working voltage in these batteries. So that's published here in Journal of Electrochemical Society. Then in a follow-up study, the year after that, they looked at how the sulfur cathode expands when you lithiate it. And so they look at the effect of adding lithium atoms to the sulfur phase during the discharge process and how that affects the voltage. And so as you can see, in general, the ReaxFF simulations agree reasonably well with the experimental results in how you get a drop-off in the voltage as you start lithiating the sulfur cathode. This lithiation process actually has been studied also with this grand canonical Monte Carlo that I've shown how that's been used to model catalytic properties in situ. More recently, there's a new development with particularly having batteries in mind. It's called eReaxFF, where it sort of adds pseudo-classical treatment of electrons back into the atomistic treatment for other atom types in ReaxFF. So There's an additional particle type, which can be an electron and a hole. And these are treated as Gaussian wave functions. So it's just a single Gaussian function. And you get two extra parameters in your ReaxFF, so we'd have to reparameterize your system. And in a proof of principle, that eReaxFF has been used to model charge mobility through aliphatic chains. So this blue blob here is an electron at t equals 0, and then you can see how that moves through your chain as time progresses. And so the calculations for the mobility in this change, not too bad in terms of what has been established experimentally for two different aliphatic chains here. So that was a proof of concept, and then subsequently it has been applied to electrolytes, or the solid electrolyte interface to be more precise, which is where you want to get a handle on how the lithium interacts with the electrolyte and what kind of processes are taking place there, and how you can get a handle on how you can make sure that your electrolyte is not being terrorized, so to say, by your electrons. So here is a reaction pathway of what's happening when you have a lithium atom and you add an electron, so that comes from the anode. The lithium can add another electron to your system, so essentially you have a 2-electron reduction here, and eventually you can split off ethylene here and carbon trioxide dianion, and so that's a reaction pathway, but you can actually see that happening dynamically as well. So let me see if we can show you that movie as well. Yeah, make that a little bit larger. So this is just zooming in on the electrolyte in this simulation. The actual simulation box is around 1,000 atoms in this case. So this is the electrolyte, that's the lithium, that's the electron, and so the electron is transferring here to the CO3, and while that's being reduced, you see that the carbon-oxygen bond here is being broken, and eventually you split off ethylene gas here. Okay, so as said, that's really new, and so there's still not many force fields. At the moment, we only have one force field for eReaxFF, which is particularly targeted towards this system here, but we expect to have more force fields available, hopefully, later on for studying different systems where you want to study the expected effect of electrons in these large, complex, dynamical systems to understand better what are the chemical transformations where dynamics play a major role in these complex systems. Okay, so that's what I wanted to show you today. So to summarize, in the beginning I spoke about using Amsterdam density functional theory, which is particularly good in spectroscopic properties and has some unique features which are useful for studying material properties for organic electronic materials, particular OLED materials. And there's also good ways of studying optical properties of nanoparticles. So we have fast and accurate TDDFT methods, making them even faster, as well as ways of dealing with molecules sitting on large metallic nanoparticles, looking at surface enhanced Raman and similar properties. Then the periodic extension of ADF band has some really interesting properties, if specifically looking at two-dimensional systems where you can treat the electronic properties as well as the optical properties. And you can also look at charge and spin transport. I didn't discuss DFTB as much, but one of the interesting features for material science could be that you could do really fast properties, albeit approximately, and you can do really fast electron transport calculations with NEGF, and that's available for most of the elements in the periodic table. Finally, ReaxFF is a even more approximate way than the electronic structure methods, but that allows you to treat dynamics of really large complex systems where you can have chemical transformations. I've discussed a few Monte Carlo techniques for speeding up your calculations, and most recently the extension to eReaxFF shows really interesting promises for studying battery materials and getting a better understanding of the dynamical properties under electrochemical conditions.